let's talk about not really a performance regression, but about a perceived performance difference and what this is. Yeah, let's dive just into a RHEL 7 versus RHEL 10 performance difference. Difference is spelled correctly. How about getting to this? I was previously presenting on the kind of research which did bring me to this issue. So for work, I got this MacBook, which I was also bringing here together with Asahi Linux. It's a nice hardware. It's RH64 hardware, and I work in support. Well, part of my work is support. Customers approach me with x86 hardware issues and software issues, so I need to replicate their problems. And for this, I'm emulating x86 guests on this ARH hardware. Sounds slow, and it is compared to virtualization, but it's reasonably fast for me. I did also investigate actually how much slower is this emulation than compared to virtualization. But let's not go into this here today. Emulation is fast enough on this 10-core RH64. Right. Along with this, I noticed when I emulate this full system, I can not only say x86, please. I can say one of all of these options, which are different chipsets, which QEMU can emulate for me, which sums up to 147 available CPUs/chipsets. So of course, I'm curious, is one of these better suited for my emulation? Is one of these faster? What's best for me? This is the kind of investigation I was doing. How to look into this, how to compare CPU performance on all of these emulated architectures. I did it like this. This is an example for doing workload on in three threads. So if I have a virtual system, an emulated system with 3 CPUs, I can put all of these 3 CPUs under load, and I get a value in the end, which is to some degree telling me how fast this CPU was doing. What is it doing in detail? This is just a bash script. It's starting 3 threads. Each of them is basically a loop doing an uncompression of a file, and when finished, increasing a counter and starting uncompression again. I'm doing this in parallel in this example here, 3 threads. I'm running this for 10 minutes, and after this, I'm summing up how many uncompressions all of these threads were doing. So after these 10 minutes, I have a number which can to some degree tell me how powerful this CPU is. And these were the results I was looking at. Higher is better. We are looking here at the completed extract jobs. And to the right, we are looking here at increasing number of parallel threads. So considering just one thread, we see that all of these did at least something like 60 extractions. These emulated systems had all 4 CPUs. I said, please QEMU, please emulate the system with 4 CPUs. So when we run the script again, with increasing number of parallel threads, we see an increasing number also in extraction jobs, up unto the 4 parallel threads. When we have more than 4 threads, then we basically want to run workloads on 8 threads, but we have just 4 CPUs. So they are more or less basically fighting against the time on the CPU, on the core, and our numbers are declining a bit. That's expected. In detail, what are all of these here? Most of these are running RHEL 10, and then RHEL 10 with different kinds of emulated CPU. And this is all of this here, the RHEL 10 variants. And then I was also emulating, I was also running RHEL 7 with an emulated QEMU. Well, this is the option, the CPU option I was using, and another one. And when we look at the numbers here, actually, the 2 variants with RHEL 10, with RHEL 7 are at the top, and the RHEL 10 variants are here. What's this one here in the middle? Emulated Haswell. Ah, no, this is actually this one here. So, what's strange about this? RHEL 7 is doing better than RHEL 10 on this one. Now, why is this? Some suspects. I'm running one hardware. I'm running QEMU as processes, and inside we have the kernel of the guest for RHEL 7. We have the kernel of the guest for RHEL 10. And we have user lands from the both Linux distributions. So we have the RHEL 10 kernel doing something interesting in the guest maybe. We have the glibc running, and we have user land code running. And QEMU running on the host might also have strange interaction with the guest. Maybe. I was tearing this down to just one single thread. Basically, you could also say I'm taking random data from dev-view random device, and then I'm encrypting this. Well, I'm compressing this and measuring how fast this is, and also this showed just with a single thread difference. RHEL 7 doing better. What are we looking at? We are looking at one single hardware. We are looking at 2 processes of QEMU. We are looking at the 2 guests, the emulated guests. And this one doing with the BZCAT doing fast. So this is again in the uncompression. And this one is doing fast. What's this V2, V3 stuff here? Intel, together with AMD, initially did a specification of x86-64. Well, I think AMD was the first one and Intel was taking it over. They came up then with one standard. Anyway, after this initial specification, what's this specification saying? If I have a CPU and it has these registers and is providing these functionalities to the operating system, then we can call this x86-64. This is what the specification is doing. And after this, we had -V2, a bit wider specification with additional registers, additional functionalities, which an operating system could expect from a CPU. And then CPU would be qualified to say, hey, I'm x86-64 -V2. And after this, even more features are covered in -V3, and then there is also V4.
Okay, I have a question. So, on the screen, I guess talking about, we talk about BZCAT, but letter 7 is fast, letter 10 is slow. I guess letter 10 is like a new version, right? So BZCAT is like a compressed function, right?
It's a user space. It's a It's a source code which was compiled. It's
compiled.
It's compiled. It's a binary which is compiled.
Yeah.
It's a userland binary.
So, but the performance is like, why the BTCAT is slower than the RHEL?
This is what I was wondering. This is what we will get to. Yeah. So we have these different flags. Why do I mention this here? So we still see this difference when we say QEMU on this side, please emulate a system which has all of the functions, also V3, also V2. We can even say V4, and also on the right side. So basically QEMU is really offering both the same system, the same hardware, so to say, and then we drop a RHEL 7 inside here and then the RHEL 10 inside here. By the way, RHEL 7 was okay just with this. RHEL 7 is running on a plain x86-64. RHEL 10, not. RHEL 10 is requiring minus V3. How can I actually find out if my CPU is compliant with V1, V2, V3? This is a nice AWK script from the internet, link here, which is looking at proc CPU info and based on this telling you, yes, your CPU is minus V3 compatible. It comes all down to AVX and various other functionality available or rather not. Yeah. So we already unified. We have the same we have QEMU emulate the exact same system on both sides. This is already no longer the issue. This here is the difference. RHEL 7 is okay with plain x86. It doesn't mind to have also V3, V4, this additional functionality available in the CPU it finds. It won't use it though. So why this difference? A bit more of this illustration. RHEL 10 is really using V3 functionality. Why are we actually then providing an operating system which is requiring V3? Because the more functionality is provided, these specialized functions, they can be executed well. So the chip maker has decided to put additional transistors on the hardware die to implement these functions because they think if someone is using them, it's probably more efficient, huh? And yes, most operations are with these more efficient. So utilizing really V3 allows us to compile RHEL 10 knowing that we will find a CPU with V3. We say we are requiring V3 compatible CPU and we achieve better performance. How reasonable is it to require V3? The first Intel architecture to implement this was Haswell, which is in the market since more than 10 years. So yes, it's reasonable to say whenever someone is installing RHEL 10, then it's probably V3 compatible CPU. How is this coming together with our problem here? Whenever we compute something here in the guest, we have something done on the kernel in the guest, and then the kernel is handing over the compute load to the layer below, which is QEMU. And QEMU is then doing the computations on the hardware below. In both cases here. But in both of these cases, the load is a bit different. Because RHEL 7 says, I'm just having a stupid CPU here. I'm doing more of the computations basically in my realm here, in my user land. And CPU is not doing as much. QEMU is not required to emulate these additional functions here. RHEL 10 though, it knows, it's compiled, optimized for V3, so it knows I will have here a CPU with these additional functions, with these additional registers. I will take full use of this. So QEMU has also, it sees the V3 functions getting triggered, getting utilized. And actually, the workload on the right side ends up being heavier from the hardware, is seen from the hardware below than on the left side. So emulating a more stupid CPU is easier than emulating a more complex CPU with more functions. This is what we are seeing here. And once we understand this, we can also do tie circle. We can also do, well, a comparison. So how about we run the RHEL 7 user land in the RHEL 10 guest? Because the kernel doesn't mind. So as of RHEL 10.0, the kernel by itself would actually also boot up on an x86-64. My colleagues said we might change this with RHEL 10.1 to 10.2 or something. As of now, just the user land above glibc and all other stuff is compiled to require v3. So we can actually run a container with RHEL 7 user land, which means glibc, the other libraries, bzcat, also from the RHEL 7. And then we get back our performance perfectly as we have on the left side. And this is why I was seeing here a different performance, a higher performance on this RHEL 7, completely emulated guest, compared to the RHEL 10 on an emulated guest. Why do we require v3 anyway? Because the CPUs, v3 compatible, are in the market more than 10 years. So it's reasonable to do this. And with real hardware, it will also bring you real performance benefits. So it's just the same thing to do. Now, discussing this with colleagues, couldn't we compile our user land and couldn't we say in the user land, couldn't we do 2 code passes and could say, so if you're running on a v3 CPU, just execute this code. And if you happen to run on the v2 CPU or older, use this other code path. And this is possible, and glibc is actually supporting it, just as it's so rarely used that we said, nah, we rather do not start to use it, be the first ones to trap into this rarely used functionality. Let's just get straight v3 requirement and do it like this. And, well, side note, Rocky Linux, for example, is compiled in the same way as we are doing this, with plain v3. Alma Linux was doing something interesting. They have done a build, just like we are, v3 requirement, and they have also a v2 build, which is an interesting move. And after some years, I hope I will remember, I will try to look at the download stats to see how much requests there was for the older build. Notably, they did also not say, hey, yeah, we are just patching, we are just hacking around, and we are doing this glibc, this GCC functionality, which is doing 2 code paths. No, this is just because whenever we write a patch for glibc, they would have to drop their mind about this and adapt this and modify the patch to fit this 2 code passes stuff. This is just too hard to maintain for them, I guess. Florian Weimer, an excellent colleague on this area, has written an article on why it's reasonable to go for v3. And this whole investigation is also nicely readable as a blog article on this link. And that's all. Any questions and comments?
Yeah, so when making improvements to Alma Linux or Rocky Link, well, clearly the way that we had rearranged for it was CentOS was always at the bottom, right? And they were trying hard to move backport. So they made CentOS Stream now on top.
Mm-hmm.
You're supposed to commit any changes and fixes to CentOS Stream rather than at the bottom. Did you manage to port it to CentOS Stream, or your
What?
your fixes or your recommendations?
I did not bring in fixes. I did discuss the situation with colleagues. There were not, so the situation was clarified, but there is no good way to prevent this in the future for others or something like this. I didn't come up with any code change which I did see which would improve this. A part of this two code passes thing, and I'm not I'm not keen on ending up being the maintainer in our distribution for this stuff. No, not if our glibc guys are saying this is a bad idea.
Are you actually seeing this on physical hardware, not just on emulation?
This difference. So on physical hardware, you wouldn't see it. You would RHEL 7 on a plain older x86 64 is running. It's also running on a V3, of course. And RHEL 10 would not run in the first place on this other hardware. So you will not really have an issue there. And also our support stance actually regarding virtualization versus emulation. I didn't say it clearly here. The world, enterprises, everybody is using virtualization. And virtualization means you have something which you want to get computed in the guest, and you can put it directly one-to-one on the host CPU, get it computed, and the result is transferred back. And emulation, we just see really in architectures and constellations where the speed is really out of question anymore. When I'm emulating in Amiga 1200, for example, speed is no longer important, and then we see emulation. And our support stance is also this full system emulation is not supported. Virtualization is done. In many reasons, by the way, we are also testing stuff which we know others are using while we are not supporting it. So, for example, if you have OpenStack setups, you would want a KVM guest, and inside the KVM guest, another KVM guest, this nested virtualization. And we say, customers, don't do this. It's not supported. But we have internal test cases to see when it breaks, because all of our support folks are using it, all of our solution architects are using it, because you can set up a system with 64 gigabytes of RAM and then have this kind of cascaded KVM running for, yeah.
I was just kind of wondering is, with the RHEL 7 is faster than the 10. What I'm wondering is maybe the CPU is doing a lot of work. When I was looking at some of the new Macs and stuff, with the newer CPU, what they're doing, like for doing videos and stuff like that, so it's very compute intense. And so what it's doing is rather than doing all the work by the CPU, it's farming out that work to all these GPUs and allowing it to do a lot faster as far as the rendering for the videos and stuff. I wonder if that's going on with the RHEL 10, and that's why it might be slower, which may mean that it's not burning up as getting as hot as some of the other ones, which might be more efficient with the newer devices. I'm wondering if that is coming into play at all.
So in our setup, this is not playing a role. We did just use the general purpose CPU functions for emulation on both of these sides. But you have a very good point, because as a chip maker, you're making a decision of rather than putting 2 further CPU cores on the die, you are saying, ah no, I'm just making the cores I have a bit smarter and I'm implementing this special functionality. We have no idea how rarely and how often it is used. And I actually saw statistics on AVX on stuff being questionably faster and also not being really performance-wise, power consumption-wise really good. So this, should I invest, should I put on my die, should I invest the silicon I have available into GPUs or into additional functionality of my general purpose CPU, or just make another core which can do everything then? This is a good question, and I can't solve this. With FPGAs, you can do this for yourself. You can design this basically and can align it. Yeah.
I think that's what's called a trade-off.
It's a trade-off, yeah. Yep.
Did you track down which particular AVX operation was the most? Because I was wondering if it's something that doesn't map well to vector instruction available on M1 and M2, or is it something that QEMU's JIT is not well optimized for AVX instruction and potentially it can be fixed?
I was wondering too. I did not do it. I could look at all of these flags which are more than in V3 minus just without V in the first ISA, and I could write example code triggering all of these functions and could have a look where we see that QEMU is doing so badly basically in emulating it. Yeah, I did not. Yeah.
You can also pass through the hardware if you wanted to, but my question was, you're saying Red Hat 10 does not work on pre-Haswell?
Pre-Haswell has no V3. It's not V3 compatible, so x86 CPUs which are not V3 compatible are not supported by RHEL. Yeah.
It's just they just don't support it at all. That's surprising.
Correct. You will get, as of RHEL 10.1, the kernel running, but userland you get then already in the installer a hang basically, because already the installer is using glibc and yeah, won't be happy. Now, you could still on your V3 compatible hardware run QEMU emulating a V3. You won't be happy about the performance. You won't be happy about the performance, but technically the stack could work, yeah.
Did you try tracing QEMU? Because the root cause of this performance degradation is TCG lack of intrinsics. So when you run x86, especially SSE or AVX instructions, they are translated into corresponding ones for AR64. So it's definitely just lack of some patterns there. You can run TCG in tracing mode and it will report that it can convert the instruction.
But was it TCG? You use an acceleration?
You can use acceleration when you run x86 on top of AR64. You can just TCG with
Oh, I see. You can actually.
Yeah, but
It's not that old. It's possible.
I think you think if we make the layer in between smart enough, then we can do better from this. But we have things which are just so one of these new functions works like this. We have, let's say, 12 registers. We are putting numbers in all of these 12, and then with one clock tick, we can have all of them increased by 1. Let's say this is one of the new functionalities which V3 is doing directly with one clock tick. Now, if you do not have this functionality, we need to do a loop which takes the first one, increases this, the second one to increase this, the third one to increase this. So the workaround logically is really much more heavy, of course, than having this functionality right directly in the. But on the other side, you're right in trying to make QEMU and first the GCC also more smarter in doing this translation of what is being done. Yeah.
Yeah.
Yep.
Yeah, recently I also learned the fact that all the all the functions provided by CPU are selectively enabled by the BIOS vendors. For example, I'm using a Hewlett Packard laptop, and also, but recently I found that the
disabled codecs.
H265 encoder and decoders are not enabled. So I'm pretty disappointed about that.
I have a hint for you. Use Linux.
I'm using it.
But the way I was reading the story is that on Windows, either the BIOS or the Windows layers do no longer allow the usage of the hardware extensions to decode these codecs. But the way I was reading the story was that the Linux libraries were nonetheless able of using the hardware in this way.
Yeah. Also I'm using a Linux. I'm using a Debian Varish distribution. So my browser has hardware accelerations. I've tested for H264, it works, and for H265 it doesn't. So it cannot play videos for the browser.
The browser is relying on the hardware either directly or via the operating system. So I would give a plain Linux distribution a try there. The way I was reading the story was that the Linux code, the Linux libraries were implementing this in a way where these were not disabled by the recent changes. Anything else on this topic? Doesn't seem so? Then we are done for this one. Thanks a lot.